All right, so let's take a look at an example problem of how we can use um, these ideas of momentum and the impulse momentum theorem to solve some problems. So let's say that I've got a baseball. Okay, so let's use the baseball example again. Let's say I got a baseball. Here's my baseball. Kind of looks like a baseball. And it's been pitched toward a batter. All right, so it's kind of coming in this way. All right, and it's moving pretty quick. We'll say that it's moving at positive 38 meters per second. 38 meters per second. Coming in this way, moving at that velocity, and we'll say that the mass of the ball is 0.144 kilograms. So I got this ball that is 0.144 kilograms. It's moving in this direction at 38 meters per second. It reaches the batter. The batter swings, and he hits the ball. And so the ball is in contact with the bat right here for we don't know how long, but it pushes the ball. All we know is that it pushes the ball back the other way. Ball's coming in at this velocity. Bat swings, we don't know with what velocity, but it hits the ball. And then after that, the ball, after it's been in contact with the bat for some amount of time, now the ball is moving in the opposite direction. It's moving this way. So negative, we'll say, because it's moving to the left instead of the right. And we'll say at 38. So the same speed that it came in, same speed that it's going out, just in the opposite direction, 38 meters per second. Now let's say part A. The question says, what impulse did the bat deliver? What impulse did the bat deliver to the ball? What was the impulse felt? So just like we were talking about in the previous video, in either case here, the impulse is what's felt by this truck when it hits the brick wall, when it changes its momentum from whatever momentum it had here at 50 miles per hour. All of a sudden it hits that brick wall, it feels an impulse which changes its momentum. So what is the impulse? What is the impulse that's given to the ball when it is hit with the bat? All right, well, if we come back up here and we look at some of the equations that we've derived here, we've got this one called the impulse momentum theorem. And actually, if we look at this, we can probably look at this first. And we can say, well, the impulse is equal to force times the amount of time that it's in contact. Well, we don't know the force. They don't tell us what the force is. And we don't know how long it's in contact with the ball. So we can't just take that. But if I look at the impulse momentum theorem here, we can take impulse, which is force times time, and we can set it equal to our change in momentum. And I can figure out the change in momentum because momentum is just mass times velocity. And I know the mass and velocity at the beginning, and I know the mass and velocity at the end, so therefore I know the change in momentum. And that's all I need to figure out what the impulse is. So let me just write this out. Force times time, which is impulse, is equal to a change in momentum. Well, change in momentum, if we rewrite this kind of the long way, change in momentum would be the mass times the velocity here, final minus initial. Whenever we're doing the change in something, it's always final minus initial. But remember, momentum is just mass times velocity. And so we're going to do the mass and velocity at the end after it was in contact. So mass times velocity final minus mass times velocity initial. Mass times velocity initial. That's my change in momentum. whatever momentum I had at the end minus whatever momentum I had at the start, and that will give me what is the impulse that was delivered to the ball during that time. So if I plug in my numbers here, mass of the ball, which is going to be the same in each case because the mass isn't, we're going to assume that the mass of the ball doesn't change when it's in contact with this, only the velocity is. So plug in my numbers here, 0.144 times the final velocity, negative 38. Got to make sure I get my signs right here, negative 38, minus, again, the mass is going to be the same, so 0.144 times positive 38. Do the math on that. We would have negative 5.5 minus positive 5.5, and so that would give us negative 11. And the units on this would actually be, so you got a mass times a velocity. So a mass, kilograms, times a velocity, meters per second. So kilogram meters per second is what we've got there. So negative 11 kilogram meters per second is the impulse that the bat delivers to the ball. All right, well, let's not stop there. Most questions don't. Most questions give us more than one part. So here's part B. Part B. Let's say we know the contact time between the bat and the ball. Let's say so if the contact time is 0.8 milliseconds, because it's not very long, milliseconds, what was the average force exerted on the ball? Well, if we take a look here, actually before we move down, so if we know that it's during this time, 0.8 milliseconds, what's the force then that the bat is putting on the ball? What is the force? Well, if we look at what we've got here, so for the impulse momentum theorem, force times time is equal to the change in momentum. We just solved for the change in momentum, so I know this part of the equation. I know the change in time. It's 0.8 milliseconds. So I have these two variables, so I can just solve for the force. Simple as that. So just using the impulse momentum theorem, force times the change in time is equal to change in momentum. So it's going to be force times, and the one little caveat here, though, the one little thing is we're gonna have to change this to seconds. It's in milliseconds. We're gonna change it to seconds. So milli, our prefix milli, and we're gonna go to our base unit of seconds. So it's gonna be 3 decimal places. So 0.8. We're gonna move this 3 places to the left. 1, 2, 3. So our new number is going to be 0.0008. So 0.00080 seconds is equal to negative 11 kilogram meters per second. Solve for the force. So divide by 0.0008 on each side. 0.0008, and the force that the ball would feel, or the force that the bat puts on the ball, we could say, would be negative 13,750 newtons. That's quite a bit of force for that ball to be feeling. So that's the amount of force the bat puts on the ball. And then let's take it one step further. As always, part C. Part C, let's say we want to find the acceleration. Find the acceleration of the ball while it's in contact with the bat. So find the acceleration of the ball while in contact with the bat. There's a few ways we can solve for acceleration, but the best way would probably be Newton's second law. Force is equal to mass times acceleration, because I know the force. I just figured it out. I know what the force is, and I know what the mass of the ball is, because the problem gave us the mass of the ball in the end, or in the beginning, and that's all I need. So rearrange this equation here to solve for acceleration. Acceleration is equal to the force divided by the mass, and so all I need is this number here in the mass. So acceleration is equal to negative 13,750 newtons over 0.144 kilograms, and the acceleration that the ball experiences would be negative 9,548 meters per second squared. So almost 10,000, negative 10,000 meters per second squared. That's quite a big acceleration for that ball to be experiencing. But that would be the final answer for that one.